Okay, this is Math 1090, section 5.2, logarithmic functions. Okay, the key idea of logarithms or logarithmic functions is that they are the inverses of exponential functions. So every exponential function is invertible, and its inverse will be a logarithm. And vice versa, logarithms are also invertible functions, and their inverses are exponentials. Okay, so we haven't, except for the very last example in section 5.1, we haven't really been solving exponential equations, and that the reason for this is simple, is because up to this point we haven't discussed. We don't have the algebraic operations necessary for solving exponential equations. Namely, we've needed these logarithm functions. So for example, consider the equation 2x equals 2 to the x equals 10. To solve such an equation where your variable is in the exponent, it requires the use of logarithms. Okay? So the first definition, a logarithmic function is a function that can be represented in the form f of x is equal to log base b of x, where the base b is some number greater than 0. And typically, the base won't be 1 either. Using base 1 is kind of boring, right? It's just a constant function, just the constant function at y equals 1. But the key idea, though, is that logarithms are inverses of exponentiation. So if you exponentiate base b, then the inverse function will be logarithm base b. Okay. So that's the gist of these next two sentences. The logarithm is defined to be the function that undoes the exponential function f of x equals b to the x. Okay, so for example, if f of x equals 2 to the x power, then the related logarithmic function is f of x equals log base 2 of x, and this has the property, well, since the exponential function 2 to the x power, if you plug in 0 into that function, then you get 2 to the 0, oops, and of course 2 to the 0 is equal to 1. And thus, the inverse function has to do the opposite, or has to create the opposite relationship. So here, the input to the function is 0 and the output is 1. So with logarithms, the input will be 1 and the output will be 0. Okay? So 2 to the 0 equals 1 is equivalent to saying log base 2 of 1 equals 0. Okay? Another way to understand logarithms, whenever you're confronted with an expression involving logarithms, you should change it into the corresponding exponential expression. In other words, when you see this expression, let me erase all this. When you see this expression, log base 2 of 1 is equal to 0, log base 2 of 1, you should always think of that represents an exponent. And the thing you should think of it as is, what do I have to raise 2 to? What power do I raise 2 to in order to get the value 1? And the answer is 0. 2 to the 0 power equals 1. Similarly over here, log base 2 of 2 equals 1, because what power do you have to raise 2 to get the value 2? A little confusing there, but you raise 2 to the 1 power in order to get the value 2. Okay? And that's perfectly reflected right here. 2 to the 1 power is equal to 2. Similarly here we have log base 2 of 4 is equal to 2, which is, you should think of that logarithmic expression as saying, what power do I raise the value of 2 to get the value 4. 2 to the 2 equals 4, as we see over here on the left side, and so on and so forth. Okay, so because the logarithmic functions are defined to be the inverses of the exponential functions, graphically we can see the relationship between these functions as mirror reflections of each other about the line y equals x. So this line right here is the line y equals x, and then we see the blue graph is the exponential function y equals 2 to the x power. The red graph is the mirror image of the blue graph across that line, and it's the function y is equal to log base 2 of x. Okay? So, for example, here we have, notice, like, for example, that the 2 to the x function goes through the point 1 comma 2 right here. And if we get its mirror reflection across that line, which is this point, which is the point 2 comma 1. So that point is going to be on the graph of log base 2 of x. If 1 comma 2 is on the graph of 2 to the x, then 2 comma 1 has to be on the graph of its inverse function, which is log base 2 of x. Okay, a few more ideas. We saw earlier that exponential functions have a domain of the entire number line from negative infinity to positive infinity, but they have a range of only the 0 and the positive numbers, so from 0 to positive infinity. Now, since logarithms are inverses of exponentiation, they're going to have the domain and range swapped. So the domain of logarithmic functions is all positive numbers. Oh, did I include 0 in the range of exponentials? I shouldn't have earlier. Anyway, so the domain of logarithm functions is all positive numbers. You cannot put 0 into a logarithm. But the range now becomes all real numbers. Okay, so see how they trade places there, domain and range. Okay, so I've touched upon this already, but the key way to understand logarithms is via exponentials. Okay, so this is the key idea. Every logarithmic statement, such as log base b of c equals a, is equivalent to an exponential statement, b to the a power equals c. Okay, so this is exactly in agreement with what I was saying before. Whenever you encounter a logarithm expression, you should think of it, okay, what power do I have to raise the base, in this case b, to, in order to get the value c? And that's exactly what you see over here, b to the a equals c. Okay, so I've put this idea into a little box here in the top right corner. The key idea is that you can always go back and forth for whichever's more convenient for you to work with. If you have an exponential, you can rewrite that exponential equation in an exactly equivalent but logarithmic equation, and vice versa. Okay, and this is the bridge. This is how you go back and forth between exponentials and logarithms. Okay, one is not better than the other. Okay, they're just kind of two sides of the same coin. Okay, so let's evaluate these logarithms. So the first one, a, we have log base 5 of 25. And I'm just going to say this, okay, what is this? This is equal to, I'm going to follow the pattern over here, and I'm going to call this a. Okay, so I want to solve this, or evaluate this rather. I want to figure out what a has to be. So I'm going to convert this to the equivalent exponential expression. So my b in this case is, my base is 5. The base of the logarithm, or the base of the exponentiation, is 5. My c is 25. So if I want to write, if I write b to the a equals c, I'm going to write 5 to the a equals 25. Okay, but what is 25? 25 is 5 squared. So a has to equal 2. So we would write log base 5 of 25 equals 2, because 5 squared equals 25. Okay, next one. Again, I'll call this A, and we've got to determine what A is. So this is the same as asking 6 to the A power is equal to the square root of 6. Well, recall that we can write the square root of 6 as 6 to the 1/2 power. So A equals 1/2, and thus log base 6 of the square root of 6 is equal to 1/2. Okay, finally, we have log base 3 of 1/3. I'll say this is equal to A. And we want to change this into the equivalent exponential. 3 to the A power equals 1/3. Well, recall that 1/3 can be rewritten as 3 to the -1 power. And so A has to equal -1. And thus log base 3 of 1/3 equals -1, because 3 to the -1 power equals 1/3. Okay. Evaluate each logarithm. Okay, I'm going to just go directly to the exponential here. 4 to the what power equals 64? Well, if I can, I want to rewrite that right-hand side as a power of 4. It turns out that 64 is 4 cubed. So this is equal to 3, because 4 cubed equals 64. Next one, I want to answer 3 to what power is equal to 243? Well, this one you probably don't know, but it's good to learn a couple of these lower powers of like 2. In this section of the course, it would be good to learn or maybe memorize a few of the lower powers of like 2, 3, 4, 5, maybe even 6. It turns out that 243 is 3 times 81, and 81 is 9 squared, so 3 to the 4th. So 243 is 3 to the 5th. So this is equal to 5. Okay, last one here. 7 to the what power is equal to 1 over 49? Well, notice I can rewrite 1 over 49 as 7 to the -2 power. And so this is equal to -2. Okay. Now we can choose any base when we create a logarithmic function, as long as the base is a positive number. Base 1 is kind of an oddball, but you could still do base 1. But there's 2 commonly used bases, and those are base 10 and base E, that number that we saw last time from section 5.1. Remember where E is approximately 2.718-ish. Okay? And we have these 2 notations. So when we talk about the common logarithm or a logarithm base 10, we just write log of x. And we just leave off the base. If the base is left off, it's implied base 10. And then this other fancy function ln of x is logarithm base e. Okay, so that's all that means. So very common notation. You'll see it even on calculators. All right, let's do some more evaluations here. Exercise A, we have log of 100. So remember, we want to turn this into the question, what do power do I have to raise the base to in order to get 100? What is the base here? The base here is 10. So this is equivalent to asking 10 to the a is equal to 100. But 100 is equal to 10 squared. So a equals 2, and this is equal to 2. The next one is, what do I have to raise 10 to get 1,000? Well, 1,000 is 10 cubed, so the answer is 3. And finally, part C here, what do I raise 10 to get 1 over 1,000, which of course is equal to 10 to the negative 3 power. So the answer is negative 3. Okay. I've already mentioned that exponentials and logarithms are inverses of each other. So by the definition of a logarithm as the undue function of an exponential function, we explicitly give the following inverse properties of logarithms. Okay, so what we're doing here in this box is we're composing together logarithm base b with exponentiation base b. And the key idea is, since these two functions are inverses, they undo each other. And in other words, when you compose them together, you get the identity function. The identity function is just a fancy name for f of x equals x. So the identity function is just the function that maps its input. The input is the output. They're exactly the same value, okay? The identity function. The identity function's graph is the line y equals x, which, as we saw before, is just that, well, for you guys it'd be this direction. The line that goes up to positive infinity has a slope of 1, angle of 45 degrees, right? And notice it is the place where you do the reflection of graphs to get inverse functions. So when you compose two inverse functions together, you get the identity function, in other words. Okay? In other words, another way to think of it is you can think of it as these are kind of like canceling each other out. So log base b of b to the x, those two cancel out and you're just left with x. Or exponentiation base b of an expression log base b of x, those cancel out and you're just left with x. Okay, so let's use this property now to evaluate these three expressions. In exercise A here, we have a natural logarithm and we have exponentiation base e. These are the same base, log base e and base e. So they undo each other, so this will just be the exponent, negative 3. So this is an example of the first. I'll give these numbers here. Okay, this is an example of the first property of logarithms there. It just looks a little different because we don't have the full word log, we have log base e. Okay. How about the next one? Exercise B. This is a case of property 2. And so exponentiation base e and ln, they undo each other. This is just 3. Finally, this is an example of property 1. Log base 3 of 3 to the 4th power. This is equal to 4. Okay, so we'll use this frequently when solving exponential and logarithmic equations. Okay, now naturally a question will arise when using logarithms. How do I actually evaluate something on my calculator? Like, what is log base 2 of 5? So what do I raise 2 to get the value 5? Well, it's got to be 2 squared is 4, 2 cubed is 8, so it's somewhere between 2 and 3, right? It's maybe 2.1-ish. Well, we can figure out exactly the value using our calculators by rewriting logarithmic expressions using either the common logarithm or the natural logarithm. So we have this first expression here, log base b of a is equal to the common log of a divided by the common log of the base. Okay? So in almost every scientific calculator will have the common log and the natural log capabilities built in. So an equivalent expression is where we just use the natural log instead of the common log. So log base b of a can also equivalently be written as the natural log of a divided by the natural log of the base. Okay, so let's use these to compute using our calculator. So this expression, log base, let me turn that off, log base 3 of 5, I'll use this one here. This is equivalent to the common log of the argument, which is 5 in this case, divided by the common log of the base, which is 3. Okay, now we'll go to the calculator and compute this. And let's see, you see the LOG button on my calculator. I'm going to do log of 5 and then close parentheses divided by log of 3. Enter. And we get, so this is about equal to 1.465. Okay? And remember, what is log base 3 of 5? It's kind of like asking the question, what power do I raise 3 to get 5? Apparently 3 to the 1.465 power is going to be very close to 5. Let's test that out. Let's do 3 raised to the power we just got. Let's evaluate this. Yeah, okay, we get a little bit of round off error in about the 10th digit there or so. But that's just because of rounding. If we were to use all the digits, we'd get exactly 5. Okay, let's compute now log base 2 of 9. This is equivalent to asking what power do I have to raise 2 to get 9? Well, 2 cubed is 8. 2 to the 4th is 16. That's too big. So it's going to be something between 3 and 4. I have to raise 2 to some number a little bigger than 3. And then I'll get about 9, right? Maybe 3.1-ish. Okay. But the way we figure this out or compute this exactly is by, here I'll use this version. We take the natural log of the argument, which in this case is 9, divided by the natural log of the base, which in this case is 2. And let's see, what do we get here? When I do, and on most calculators, the natural logarithm is ln. Okay, so we're going to do the ln of 9 divided by the ln of 2. And we get about 3.17. If I round to the third place, 3.170. Okay. And let's try it out. If I raise 2, remember this is equivalent, if I say this is a, then this is equivalent to saying 2 to the a power equals 9, right? And we just discovered that a is 3.17-ish. So let's do that. So 2 raised to the value we just got, and evaluate that. Yeah, we almost get exactly 9. We're just off in the last digit there. we get just below 9. Okay. By the way, on your, if you have a TI-83 or TI-84 calculator, you don't even really need to remember, you should remember this change of base formula, but these calculators, if you go to math, and if you go, let's see, I think if you go up one, oh, there it is. Choice A, log base. So in the math menu, if you choose log base, this is also in your catalog of functions. It'll allow you to put the base in. I'll put in 2, cursor over, and I'll put in 9, and enter. There you go. We get 3.1699 just like before. Okay? So these calculators have this kind of nice feature built in that they can compute this. Okay. I'm gonna pause there.